Hello everyone, I am Bhaskar De and today is the problem solving session, 8th problem solving session for the course Introduction to Lasers. And today I am going to discuss about pumping pathways. So the what is pumping pathways? So basically when we talk about laser, there is a lasing action that is taking place. So before that there is a population inversion happens in the system, and that is known as the pumping. So pumping can be of the form of anything, like you use another laser to pump that particular system, or use some kind of other light source or some thermal sources to pump that system. So pumping means that you basically excite the ground state population to the excited state, and then there will be the lasing action by relaxing those population to a lower level. So the pumping pathways is basically how the pumping is done. So for different kind of laser, the pumping pathways are different. So there are, if you classify the pathways, then it will be broadly classified in two category. One is direct pumping, another is uh, indirect pumping. So two types of excitation pathways can be used to produce pumping of the upper laser level. Now there are two ways. One is direct pumping, and the second is indirect pumping. So this is also known as pumping and transfer. So today, one thing I will say that today is not a very specific problem solving session, but this is a I'm going to discuss this concept because this is very necessary concept to know before you go into different kind of laser. So there are different laser available in the market, that is like titanium sapphire laser, helium cadmium laser, helium neon laser, argon ion laser, CO2 laser. So there are different kind of laser, and every laser has their own pumping mechanism. So that's why these pumping pathways are very important. So there are two types of pumping process, that is one is direct pumping, another is indirect pumping, where there is the pumping and transfer. So in indirect pumping, as the name suggests, that it is not exactly directly you are sending or exciting that ground state population to the excited state, rather than the two state that is participating in the lasing action, that is indirectly pumped. So basically other excited state is being excited or being populated by the pumping, but that population is transferred to the upper lasing level. Okay, so first I will discuss about the excitation by direct pumping. So in the direct pumping process, the excitation flux is sent directly to the upper laser level form a source or target state J in which the source state is the highly populated ground state 0 of the laser species. So basically let's assume that there are this kind of states. So this is the ground state, this is the upper state, and this is the lower state. Now the pumping is done like this. Okay, so this is the pumping. So this pumping is done from the ground state to the ground state or zero state to the U state, and the lasing action is occurring between this. So this is the lasing action. So the lasing between U and L. So by direct pumping we want to mean that the upper excited state is directly pumped. So basically the population is sent from 0 to U directly, and this U is actually the excited lasing state. Okay, so here there are two kinds of pumping. One is optical pumping. So optical pumping is the process most often used for solid state and organic dye laser. So already you have some example. So solid state and organic dye. So these two lasers are being pumped by optical pumping. So the excitation involves absorption of pumping light. So here the pumping is done by light. So here the pumping is done by another laser or some kind of light source that actually excites the zero state to send the population to U state. So the rate can be written in form of B0U. So the I is the intensity of the optical pumping. So this is the optical pumping, and then there is another pumping that is known as particle pumping. So particle pumping is generally used for gas lasers and semiconductor lasers. So basically these two pumping are so optical pumping is used for solid state laser and organic dye laser, and the particle pumping is used for gas laser and semiconductor laser. So these are the different category of lasers. So here the same thing can be written in form of NPK0U, where NP is the particle pumping particle density and K0U is the reaction probability for a transition from 0 to U. When a particle P collides with the laser species in level 0. So basically the definition is little different. So from here, for particle pumping it is just NPK0U. So NP is the pumping particle density and K0 is the reaction probability for a transition from 0 to U state when a particle collides with the laser species in level 0. So basically here the material or the medium is actually bombarded with some particle, and the energy or the pumping is happen when there is a collision happen between the particle and the laser species. So that is like the energy that is transformed in the system is basically comes from the collision. So now this parameter can be written in different form also. So basically if we want to write it in terms of the cross section, then we can write this as Ne. So this is for gaseous discharge. So this is basically the laser is, the system is basically bombarded with electron, so that will make this transition happen. So when you, so this kind of things is used in argon laser and so on. So they are basically use the electron source and then that electron collide with the medium and then we have the population inversion. So this is the electron density. This thing is the velocity, average electron velocity, and then sigma is the velocity. This is the cross section. So this is the this is the velocity average electron excitation cross section for the from the level 0 to U. Okay, so now you can if you look at this diagram, you can see that this is a very straightforward process, because you have to just excite the zero state, and you have to pump the zero state, and all the population will go to the u state, and then there will be a lasing action that will take place from u to l. So this is a very straightforward and simple technique, but there are many disadvantages of this process, because so the first disadvantage is there may not be any direct route to reach um, level u from 0. So that means that from optical pumping you cannot execute this kind of pumping, because then this coefficient will be very small. So b0u is very small, so very small, and on the other hand 0u is very small. So this is for the optical pumping, and this is for the particle pumping. Okay, so these two things are very small, so that means that there will be no gain. So that means that though the mechanism of the pumping is very straightforward, but in reality you will not have that much gain that will actually help us. So the second disadvantage is that is that okay, let me draw the diagram again. That this is the previous diagram we are using, that we are populating the u level. So this is the desired process for direct pumping, but it can also happen that this transition 0 to u is less probable than 0 to a. So basically when you try to pump the medium, that is actually pumping this one. So if the level L is populated like that, then there will be no lasing action, because you are not reaching the level U. So there will be no lasing action, and that makes the direct pumping useless. Now here you can see that there might be no direct route to reach the level u from 0. There might be direct route to reach level u from 0, but the chance of reaching L from 0 is larger than the chance of reaching u from 0. So I'll just so from 0 to L is much more probable than 0 to u. So these two are the disadvantages. And then even though there may be a good probability of the for excitation via absorption of either pump light or electron excitation, but there might be another thing can happen, that the intensity of the pumping may be very low. For example, like we need to pump from 0 to u, so we need to give this much amount of energy, but for some reason the intensity of giving this kind of energy is very low, then this direct pumping will cause a error, so there may not be a good source of pumping flux available. There may be good source. So then so that means that insufficient intensity insufficient density. So intensity for optical pumping, this is for or you can say for electron. So basically, like if even if you have a direct route to reach u from 0, and even if you and also if there is a chance that the probability of reaching u is greater than probability of reaching l, then still there is a chance that the good pumping source is unavailable, and that will cause that the direct pumping is inaccessible. So that so now the third problem can be visualized like this. So there are two systems. So now this is the delta E u0, but here this is the delta E u0. So these are the two systems where you can see that this delta E u0 is large and this is small. So for this particular system, direct pumping is very useful because you need to have very small energy. but in this, for this case, the delta EU0 is very large. But again, if we see that the so here the difference between U and 0 level and the difference between U and L is almost same, or the two spacings are not that far apart, but here this is far apart. So here you can pump with a different wavelength and get the lasing action, but here you have to all pump the laser with the material with the almost same wavelength. So these are the problem of the direct pumping. Now the next thing is excitation by indirect pumping. So now the because of the restriction of direct pumping I have mentioned, so multiple step pumping process, or this is referred as indirect pumping or pump and transfer, is necessary. So the as the name suggests, this is indirect pumping, so that means that we are not directly exciting the U. So if you look at this diagram, then in direct pumping we are directly exciting the level U, but in indirect pumping we will not directly excite the U level, rather than we will excite another level or any adjacent level, and then that population will relax or transfer to the U level, and then the lasing action will take place. So this is just going the same place by an alternate route. So there are three kind of uh, indirect pumping. So what happens in the indirect pumping, we have another level Q. So here it is a 3-level thing, but in case of indirect pumping that will be a 4-level system. So this is the 0 level, then this is the Q level, so this is the transfer, and this is the laser action. This is U. So here what is happening, that we are exciting the Q level, not the U level. So we are exciting the U level. So that means that we are exciting the Q level by Q level. So we are exciting the 0 to Q, and then there is a transfer of population from Q to U, and then we have the lasing action from U to L. So that's why this process is known as pump and transfer. So the pumping is happening between the 0 to Q, transfer is happening between Q to U, and then laser is U to L. Okay, so this process, so this is one kind of pump and transfer or indirect pumping, and this is known as transfer from below. Okay, now there is another process, indirect pumping process, that is, so this is 0, this is Q, this is U, and this is L. So this is basically here the pumping is done from 0 to Q, as I mentioned in the earlier diagram, but here the transfer is like this. Okay, so basically from here to here the population is being transferred. So this is known as the, and then we have the lasing action here. Okay, so this is known as the transfer across. So basically it is not transferring from below level, it is just transferring the population from one level to the another, and the two levels are residing at the same energy. So this is basically transferring the population from one system to another system. Okay, but though this is like I have added only one extra level and explaining the indirect pumping, but this is very simplified version of indirect pumping. But in reality, or in the real laser, the pumping process is much more complicated than this. There are multiple levels that is being pumped, and then we have, then there are certain transfer takes place, and then we obtain the lasing action. Then these are the two pump and transfer process. Then there is another process, that is the, this is 0, this is Q, then there is 2 level, this is the pumping, this is the transfer. So this is known as transfer from above. Okay, so now the advantages of indirect pumping. So So now the thing is that the pumping this Q level is maybe a single step process or a multi-step process, like you are pumping from one level 0 to sorry, so 0 to 1 level and then pumping that level to Q and so on. But generally and mostly this process is a single step process, and then that in this kind of pumping the Q level is closely located in energy to the upper laser level, so that is U. So this gap is very less, so that's why this transfer process is very easy to occur. So it is, so basically here we can use a convenient pumping source to pump from 0 to Q, and then the population will be transferred from Q to U, and that will make the pumping or the process of population inversion much easier. So in some cases what happens that the lifetime of Q level is much larger than tau U. So basically the lifetime of U is larger, the lifetime of the level Q is larger than the lifetime of U. So that means that the population that is in the Q level will stay for longer time here. So that means that this makes the level Q as reservoir. Okay. The second advantage, in some cases the pumping probability for pumping from 0 to Q is much greater than that from 0 to U. So this is the problem, one of the problem of the direct pumping, but it is addressed in the indirect pumping, is that by using the logic that if there is a chance that pumping from 0 to Q has a better probability than the pumping from 0 to U. Okay, so this is a very good thing to happen for a laser, that this will significantly lower the pumping requirements. So this will, now the third advantage is transfer from Q to U can be quite selective in many cases, which implies that it occurs much more favorably to upper laser level than to lower laser level. So in one of the disadvantage of direct pumping is that the pumping can happen between 0 to L rather than 0 to U. Okay, so this transition is much more easier than the actual pumping 0 to U. So Here the transfer from Q to U can be quite selective in many cases. So that means that if we that in indirect pumping we can actually select if we want to pump from 0 to Q or 0 to L. So here that doing the pumping from 0 to Q is much easier. So basically if the transition 0 to Q to U is selective, then we can understand that the pumping to U level, indirectly to U level, is easier in this case, in that case. And then even if there is a chance of pumping to 0 to L, we can avoid that scenario. And this is the most common scenario for indirect pumping, that the level Q can belong to a different species of material. So this Q can belong to a different species of material than U. So this could allow the use of a material that can be efficiently excited to the storage level Q. So Q, so basically there are two material that is like mixed or something happened to them, like you talk about Nd:YAG or erbium doped laser or all those things. So they are basically, you have the level Q from one material and the U from other material. So the stored energy is then transferred over to the laser level, either by a collisional or a radiative process. So basically this process can happen collisional or a radiative process. Then the level Q can have a very broad width and thus accept pumping flux of intensity over a broad range of energy. So that means that the exciting to the Q level is very easy rather than exciting to the U level. So Q can be a very broad band type of thing, so that will allow the broad range of energy. By using the broad range of energy, we can pump to the Q level. So using this method, uh, the Q level is actually very broad in solid state laser. Let me just write the point. So that means that this Q level capability, so this Q level is very useful for solid state laser, where the level is very broad and then that actually pumped with the flash lamp. And as you know that flash lamp is a very broad has a very broad energy range. Now we'll go to example specific scenario. So it is a specific pump and transfer process. Okay, so the first thing we are going to know about is transfer from below. So transfer from below generally occur in the gas lasers. So here the level Q is excited with some method, and then there is a electron collision, and that will excite that will transfer the population to the upper laser level. Okay, so that argon ion laser. So in argon ion laser there is this level 0 Q U and L. So this is 0 air and Q, this is of air plus, then this is U, this is L. So this is the pumping from 0 to Q, that is done by electron collision. Electron collision, then another electron collision takes place, and that will cause the transfer to happen. And then we have the laser 488 0 nanometer. So this is the ground state of argon ion. This is the ion ground state. This is the atom ground state. This thing can also be seen in another thing, that is selenium soft X-ray laser. So in argon there are two stages of ionization is included. So this is the first ionization by electron collision, and then this is the first ionization step, this is the second ionization step. But in the selenium there are 24 stage of ionization. So in case of selenium, the laser has a wavelength of 20.6 nanometer, and again if there is another step of ionization in argon, then we will have another lasing action, and that will be of 363.8 nanometer. This is happen from argon 2 plus, and this is happening from argon plus. So this is for argon plus, this is for argon 2 plus. So AR plus, AR double plus, AC24 plus has a transfer from below. So this three laser has this, use this in indirect use this kind of indirect pumping, that is the transfer from below. Then we will come to transfer across. So this also happen in the gaseous media. So the transfer cross will mean that the intermediate level Q has the same energy as the upper laser level U. So basically we are not directly exciting the upper laser level, rather than we are exciting another energy level that is has the same energy as the upper laser level. So in gases, energy can be transferred via a collision between two atoms and molecules, but the process must conserve both energy and momentum of the combined two-body system. So here two well-known lasers that operate in this process are, one is helium neon laser and another is CO2 laser. So basically in helium neon laser what happens is that this is the helium ion, the helium, and then this is the neon laser levels, the upper laser levels and lower laser levels. Okay, so the pumping is done from here to here, that is like 0.8 eV, and then the transfer occur, and then we have the lasing action. Okay, so basically if we go in more detail of helium neon laser, then that will become like this, that we have three levels of helium, and then there are other two levels, and then there there is a level in the middle, and then there is a lower level, then we have the ground state of neon. So for helium, the pumping is done from there to there and there to there. So these are, if we use the spectroscopic term symbol, this is 1s0, this is 2 3s1, this is 2 1s0, and then this is the neon. So this is the 5s state, this is the 4s, then this is the 3p. So from here to here, this transition is the well known 632.8 nanometer, and this transition is 1.15 micrometer. Then we have a very fast decay from here to here, this is the 3s, and then another decay here, that is so this is the visible and this is diffusion. So if we want the details of the mechanism in helium neon, then this is this kind of complicated. So there are two transfer across occur, one is in here and another is here. So basically here, if we want to look for the Q state, then we have two Q state, one is this and another is this one, and then there is two transfer across processes happen, and that will populate the 5s and 4s, and from 5s and 4s we have a lasing action to 3p, and then there is the decay from 3p to 3s and then to the ground state of neon, which is 1s0 to p6. So this is the process of helium neon. Now come to the CO2. So in CO2 there is the CO2 is mixed with nitrogen, and basically we use the vibrational states of nitrogen to actually pump CO2 laser. So the energy diagram is like this. So this is for N2, this is for CO2. So these two are ground state. This is the pump. So the pumping is done by electron collision in nitrogen atom. So that will pump the excited state of nitrogen. Then there will be a transfer. So this transfer is also collisional transfer. Then we have the lasing action, that is the 10.6 micrometer laser, and then there is a fast radiative decay. So these are the transfer across process. Now we will come to the transfer from above process. So for this process, the two laser I am going to talk about is very famous. One is the UV laser. It is the first 4-level laser actually, and the second is UV laser is very old and it dated to something around 1970 or something like that. And then there is the ND YAG laser. ND, so now the interesting thing about the so in UV laser what happens is that there is a pumping band. So here you are not pumping a single level, rather than you are pumping a band. So that means that you are pumping from here to here and also from here to here. So you are pumping these bands, and then from these bands the population is transferring to a lower lying level, that is U, and this is a non-radiative decay. That's why this is uh, indicated by this curvy line. And then from the now the as the U level is populated, then the lasing action takes place from U to L, and we have this 694.3 nanometer laser. Then again the same thing happen in the ND laser. The full form of ND is neodymium. So in that case, so in ND laser, this is the ground state, the GS, that is 4I9/2, and then there is a pumping band. So basically the Q is not a single level, it is a total band. So that means that, as I mentioned earlier, that when you have a band at Q, then it makes easier for to pump that bands. And then there is a non radiative decay. So this is the transfer. So this you can see that this is a transfer from above, and then we have a lasing action, that is this 1.06 micrometer. So now the lasing action takes place between the level 4F, sorry, 4f 3/2, and this is 4i 11/2. This is 4i 9/2. Okay, so this is how the transfer from above is happening. Now this transfer from above process happen in semiconductor laser also and in dye laser also. So in semiconductor laser, what happens is that you have a n doping side and a p doping side. So for n doping, the energy bands is like this, and then and p doping, that will be a little lower. So from here to here, the transfer is takes place, and then we have this laser action. Okay, so this is for the semiconductor laser, and then there is the dye. In dye, you don't have a have levels, you have a band, so that means that you have this kind of thing. Okay, so if you have this kind of thing, the first, so this is the Q and this is the L. So when you have this kind of thing, the thing that happens is this. So you have, when you pump this system, you have multiple pumping, and the band is occupied with a different density. So basically it is possible that you populate the upper level of the band more, and then and less the lower level. So that means that these bands are unequally populated, and that will, and then the then you have the transfer process, and then we have the laser. Okay, so this is the U. So basically the lower level of the band is acts as the upper laser level in dye laser. So you can see that in the dye laser, this is like very easy to pump that laser, because the pump can be of any range, because we have a band for Q and a band for L. So that means that we can use a broad energy range to pump that particular dye laser, and then all the population from the levels of Q band will comes down to the U level, that is the lower level of the Q band, and then we'll have a laser action from U to L. Again this population, so this is for the dye laser. Again this thing happen in excimer laser. If you have heard about this laser, the same transfer from above process is happened in the excimer laser. And then there's another kind of laser, that is plasma recombination laser. So here basically you don't pump in atom or something like that, you pump the from ground state to ions, and then those ions are cooled down to another bunch of ion, and then there is a recombination of ion, and then those ions comes down to a single upper laser level, and then we have the lasing action. And in excimer laser we have krypton and fluorine ion, and they form the excimer, and then from the transfer is basically the excimer formation. So the transfer is happened when they form the excimer, and then we have the lasing action. So these are different kind of process for different kind of laser, but as you can see that in most of the cases we see the transfer from above. So now another more realistic example for Nd:YAG laser. So for a certain case we have these states for Nd:YAG. This is 4i 9 by 2, this is 4f 5 by 2, this is 4f 3 by 2, this is 4i 11 by 2, so this is the 808 nanometer gallium arsenide pumping diode. So here it is pumped with the diode laser, that is the 808 nanometer gallium arsenide pumping diode, and then from there we have a non-radiative decay from 4f 5 by 2 to 4f 3 by 2, and then we have the lasing action, that is of 1.064 micrometer or 1.064 nanometer basically, ND here. Okay, and then from 4 so the lasing action occurs between the 4f 3 by 2 and 4i 11 by 2 levels, and then from here we have a non-additive decay from 4i 11 by 2 to 4i. So there is a there are also other laser, that is ND YVO4 YB YAG laser. So these are different kind of laser, but the fact is that these are quasi 3 level energy configuration. But one thing that I like to mention, and that is very interesting fact about this particular wavelength, that this wavelength is actually very dangerous for our eyes, because as you know, our eye have a lens kind of thing, that is this pupil, or that is the lens we have in our eyes. So that lens actually focus that this particular wavelength is at the back of our plane where the image is created when we see something. So basically, if we see at this particular wavelength directly on a laser, then we can have a permanent burn in our eye. So that is a very difficult dangerous wavelength to work with. But the thing is that every laser is very dangerous basically when we use a class 3 or class 4 laser. So if you have seen any laser, you can see that there is a mark of dangerous mark on those laser equipment, and written it is a class 4 product or class 4 laser. So those laser are very high power laser, and those can actually burn and cause permanent damage to your eyes, and also it can damage to your skin, but the damage in your skin is repairable, but in your eyes that is not repairable. So whenever you go to a lab, please be very careful about it. Now, as I am mentioning a lot of electron collision pumping, so let's just write down some laser discharge temperature. Laser charge. So this is neon. So this, all these are in Kelvin units. So neon, for neon it is 400 Kelvin. Air plus argon ion is 1500. Cu is 1800. Cd is 600. Ac23 plus is 6000000. CO2 has 400, and then KRF, krypton fluoride, that is also has 400. So these are some temperature of the discharge tube. So this discharge tube is used to generate the electron, and then those electron actually collide with the laser material, and then we have the population inversion or pumping. Now I will change the topic and go to another interesting thing, that is, this is going to be basically a information based topic. So also this part was kind of information based because these are just information for your knowledge, but from here you can understand the how these lasers are actually pumped and then the lasing action takes place, and try to remember this wavelength because there is a chance that you will be asked the wavelength of these particular lasers. And maybe you have some kind of MCQ question where you are asked that what kind of pumping is done for semiconductor laser or in any other laser, or you can ask that which of the following laser is uh, follow the transfer from above process or transfer from below process for pumping. So in that case you will can answer those MCQ question, because MCQ question are basically based on the information either it is true or false, or you have four options. So in order to answer the MCQ question you need to have this kind of information stored in your memory. So in the car mirror cavities, so there are different kind of car mirror cavity, but first one is on the plane parallel. So here R1 is infinity and R2 is infinity, and the distance from here between two mirror is D. So this is the plane parallel cavity. Again there is a similar kind of thing, that is so it is also looking like the plane parallel, but it is actually not plane parallel. It is R1 is much greater than D and R2 is much greater than D, so it is not infinity. So these are not plane mirrors, these are actually curved mirrors, but the as the radius of curvature is very big, that's why it's looking like a plane mirror. Okay, so this is known as long radius cavity. Then we have this one, this is known as symmetric. So for symmetric it is R2 greater than D and R1 greater than D. So this is the symmetric cavity. Then the R1 is greater than 2D, and here it is R2 equal to infinity. So at one side it has a curved mirror and another side it has a plane mirror, so that makes this as So this makes this as half symmetric. Then this is symmetric confocal, R2 equal to D and R1 equal to D, and this is A by root 2. So this is basically a curved mirror with a radius of curvature D for both the mirror, and this is known as symmetric confocal. So this is actually makes the size of the beam as A by root 2 at this particular point. That's why it is known as symmetric confocal. Then at one side it has a curved mirror, and at another side it has a plane mirror, and the radius of curvature is R1 equal to 2D. So this is the half symmetric confocal, and the A by root 2 is here. Then R1 greater than D and R2 equal to minus R1 minus D. So here we have a concave convex combination. So this one is concave, this one is convex mirror. So this makes the concave convex cavity. Then so this is near concentric R2 d by 2. So this here the two mirrors has the radius of curvature d by 2, and this makes that near concentric cavity. Again, so here R1 equal to D and R2 equal to infinity, and this is known as hemispherical. So these are all the two mirror laser cavities. So here all the two mirrors are used in the cavity. Now after mentioning all those cavities, we can actually use the matrix method to calculate and extract the information, and also extract the stability information of the cavity. But I have done that in one of the earlier classes, so I will not do that again here. Now I will go to a new one to example. Suppose we have a 441.6 nanometer helium cadmium laser operating in TM00. So suppose we have a 441.6 nanometer helium cadmium laser operating in TM00 mode in a half symmetric laser cavity that features a distance d between mirrors of 0.6 meter and a radius curvature r of the mirror of 2 meter. So basically we have a 441.6 nanometer helium cadmium laser operating in TM00 mode. The laser cavity is half symmetric, so that has the 2 meter has a distance of 0.6 meter and the radius of curvature r of the curved mirror is 2 meter. So now we will calculate some thing. That is, first is the minimum beam wedge, that is omega naught square. So for half symmetrical cavity, if you look out for formula, we will have this formula, that is lambda by 2 pi 2d minus 2r minus 2d to the power half. Then 441.6 nanometer by 2 pi to 1.2 meter. So this is equal to 1.38 into 10 to the power minus 7 meter square. So the omega naught is 0.37 mm. Now we will calculate the volume of the TM00 mode, so that will be denoted by V00, that is pi omega naught square by 2. So this is the area of the beam, and then d, so that will be pi into omega naught square by 2 multiplied by d, so that will be pi into omega naught equal to point 0.00037 whole square 37 square by 2 into 0.6. So this will be 1.29 into 10 minus 7 meter cube. Now the photon energy for this, so if you check about the helium cadmium laser, that you will have the wavelength of this as 441.6 nanometer. So the photon energy is basically 6.63 into, this is the value of the h, that is the Planck constant, then the velocity of light divided by 441.6 nanometer. So this will be 4.5 into 10 to the power minus 19 joule. So basically this is has a factor of 10 to the minus 19. So basically if you can convert this into EV, that will be a better unit, but for now we'll good enough with joule. Now we have to obtain the power radiated from the mode volume. So Nu E00 AUL H nu UL. So now this Nu and AUL can be obtained from the information about the laser, which is not given in the problem, but I will just use. But don't worry, then the exam you will be given with all the necessary information to solve the question. So the value of Nu is 4 into 10 to the power 16 meter cube inverse. Then V00 is calculated 1.29 into 10 to the minus 7 meter cube. Then the AUL is 1.4 into 10 to the power 6 second inverse, and then the H nu UL is 4.5 into 10 to the minus 90 joule. So after doing all the multiplication, we will have 3.25 into 10 to the power minus 3 watt. So it is 3.25 milliwatt. So the power available from the laser is 3.3 milliwatt. Now another topic, the very short topic I'll just mention briefly, that is the unstable resonator. So unstable resonator. So we are talking about stability of the cavity resonator and all those things, but here we are talking about an unstable resonator. So this is a type of laser resonator that can provide useful laser output with a reasonable beam quality without meeting the criteria for stability as discussed previously. So you don't need to meet the stability criteria, but you have to have a provide useful laser output with a reasonable beam quality. So this kind of resonator are used to obtain high power output with a Gaussian shaped beam from a laser medium. And so these are very high power laser. So that I was talking about the class 4 laser and all those things. So this all those laser has this kind of resonator. Now for unstable resonator, okay, so this is the gain medium, and this is the output beam. So you can see in the unstable resonator we have basically leakage around the mirror. So basically this beam is going back and forth, and then we have a leakage from here and here. So a suitable unstable resonator cavity design, this leakage around the mirror can become a useful intense laser beam that has a nearly Gaussian shape profile. So leakage around the mirror So basically here in normal stable resonator, what we use has the beam, we use the beam that emits from or get out of the resonator. We use the beam as a whole, but here we are actually using this part. This part, so these parts are referred as leakage. So now this leakage around the mirror can be used as a very intense laser beam, and that has not exactly Gaussian shape profile but nearly Gaussian shape profile. So now there are certain requirements and conditions associated with the unstable resonator. So the first one is that the volume of the amplifier is associated with the region in which stable modes would occur is too restrictive compared with the amplifier dimension. So that the amplifier, the width of the amplifier is not supporting the stable mode. So that is the volume of the amplifier is not support the stable modes. So that is the restriction. So I can write that the second thing is very high output is required. So high power output from a large gain volume is required. So this high power output is of a very high watt, like a megawatt or terawatt, something like that. So a very high power output from a large gain volume is required. The gain of the medium is high enough that stable low order modes do not have sufficient time to evolve before the gain is depleted. Okay, so the gain of the medium high enough that stable low order modes do not have sufficient time to evolve before so the gain of the medium is high enough that stable low order modes do not have that much of time to evolve before the gain is depleted. So that all the gain that is available will go for higher order modes. Now such a high gain also makes it possible for every laser to operate in spite of the high diffraction losses of unstable cavity. So even there is a certain diffraction loss in the unstable cavity, this high gain will be used to have a very high output laser. So there is a ratio that is defined as MUS, the magnification ratio of unstable cavity resonator, that is RR by RO. So this is the radius of curvature of the large diameter rear mirror, and this is the smaller mirror. So this is the radius of curvature of the large diameter rear mirror, and this is the radius of curvature for the smaller mirror. So this is the magnification ratio, and for unstable resonator, the condition we need to follow is G1 G2 is greater than equal to 1, that is known as the positive branch, and G1 G2 less than equal to 0, that is known as the negative branch. If you recall that there is a condition of G1 G2, this is known as the stability condition, where G1 equal to 1 minus d by r1, that is 1 minus d by r0, and G2 equal to 1 minus d by r2, that is 1 by d by r1. Okay, so I got a problem with the connection, so anyway I'll just repeat the part here. That is, the for unstable resonator the condition is G1 G2 greater than equal to 1, that is the positive branch, and for G1 G2 less than equal to 0, that is the negative branch. And we already know that if you can recall that the stability condition for a resonator was 0 less than G1 G2 less than 1, where G1 and G2 are G1 equal to 1 minus d by r1, and that is 1 minus d by r. So G1 equal to 1 minus d by r1 equal to 1 minus d by r0, and G2 equal to 1 minus d by r2, which is 1 minus d by rr. So rr is the radius of curvature for large diameter rear mirror, and the r0 is the radius of curvature for the small mirror, which you can see. So this is the rr and this is the r0. So with this I will stop today, and then I will solve some problems in the next class, that is in the next Friday. So we'll meet again on the next Friday. So I'll end this class here. Thanks for joining.